Hello, so let's start the second part of the class dedicated to atomic structure and interatomic bonding. So to summarize what has been studied during the first part of the class, so we'll remember some basic concepts about the atoms, about the atomic structure. We introduced the quantum, the four quantum numbers, electronegativity, also the periodic table. And after that, we introduced the different kind of chemical bonds. So we distinguish the primary chemical bonds and the secondary bonds that are called also physical bonds. So within the primary bonds, we describe the ionic bonds, covalent bonds, and metallic bonds, and we explain from which kind of atom they are obtained and how do they are formed. And we also presented the secondary bonds, and we saw that the hydrogen bonds are the stronger one. We have also the dipole-dipole, induced dipole-dipole, that create some interaction between two molecules without exchanging electrons. So now let's introduce the bonding energy. So first, we should consider two atoms. And so we will consider them and different interatomic distance between them and wonder what is happening, what are the interaction between them along one axis. First, if we consider that they are very far one to another, so we can consider that they do not feel the influence of the other. So in fact, they do not interact. And then if we approximate, if we force these atoms to come closer one to another, so they will feel two kind of forces, an attractive force and repulsive force. And in fact, we won't get in deep explanation right here, but up to a certain interaction separation, so they will begin to attract each other. So the electron of one atom will be attracted by the positive charge of the nucleus of the other atom. And eventually, depending on the kind of sharing of electrons that they can have, depending on all the criteria that we saw before. So their electronic cloud will begin to interpenetrate. And if we push even more these atoms close to another, so the nuclei will begin to feel the presence of the other nuclei. So positive charge will begin to feel the presence of positive charge of the other nucleus, and we will have a repulsion of these two atoms that will occur when we will try to push and to approximate even more the two atoms. So when we are considering the position of these atoms, we consider the center of their nucleus. Okay. So if we want to represent it in a very mathematical way, so we can write down this equation. So the resulting force between these two atoms is equal to the attractive force plus the repulsive force. And now if we represent graphically what is occurring according to this interatomic distance or interatomic separation. So as represented on this graphic, we can see that at very long distance, as we saw, we have no influence of, between these two atoms. And we will approximate these two atoms, and we will have the contribution of an attractive force and of a repulsive force. So to have an idea of the kind of resulting force obtained, so we should sum up the attractive force due to these attractions that we described between these two atoms and the repulsive force between the two nuclei of these two atoms. And so the net force is given by this curve right here, so the plane curve, and we see that there is one specific point at which the resulting force is equal to 0, which means we found an equilibrium distance between the two atoms. So no force, which means that the atom will not try to separate, and they will not try to attract each other even more. So this repulsive force equal to 0 corresponds to a specific distance, which corresponds to what we saw right here, which correspond to R0. Okay, so at R0, this interatomic distance, specific interatomic distance, there is no resulting force between these two atoms. They are at equilibrium. Okay, so it can be more convenient to talk about, it could be more convenient to talk about energy than to talk about forces. So now let's have a look to the potential energy. So to get the potential energy, we should integrate the forces in relation to this variation of the interatomic separation. And so by doing that, mathematically, we obtain the graphic presented above. And as you can see, so the resulting energy, potential energy, as a function of the interatomic separation, give us this energy well. So what we name energy well, which means that we have a minimum of energy at a specific interatomic distance. And this interatomic distance, which corresponds to the minimal energy, is in fact the interatomic distance at equilibrium. So in fact, these two atoms are in equilibrium, and at this position, we have a specific energy between them that is given by the minimal point of this potential energy well, which is called bonding energy. So we write it E0. Okay, so if I have such kind of graph, I can determine what is the bonding energy between two atoms and what is the interatomic distance between them. Okay. Okay, so approximately, in fact, the interatomic distance is the distance corresponding to the point of minimum energy that we presented and correspond to the sum of the two atomic radii. So for pure metals, since all atoms have the same atomic radius, we can determine that this interatomic distance at which the energy or the energy is minimal, and also the resulting force is equal to 0. So it's the same thing, it means the same. So this distance is equal to 2 times the atomic radius. Okay, and in the case of ionic solids, so since ionic bonds are formed by two different atoms, so one which is more located in the right part of the periodic table, and the other one to the other side of the atomic table. So we should consider that the radius is very different. And in that case, the interatomic distance is equal to the sum of their radii. So this little r for the smaller atom, and the big R for the biggest atom. Okay, and now what is the relationship between these bonding energies and some of the materials properties? So let's have a look in order to understand the importance to know the bonding energies and how we can predict some of the properties of this material when we know their bonding energy. So the shape of the curve, of this curve, is directly related to the properties of the material, and one of them is related to, in fact, the elastic deformation. So what is elastic deformation? So during this class, when we are going to talk about mechanical properties, we will go deeply in the understanding of elastic deformation, but basically it is manifested as a small change in the interatomic distance and energy of the bond. So it is when we stretch a material, so typically an example of elastic material, which is rubber, for example. So when you stretch it, you apply a force, so it's stretch, it's deform, and when you remove the force, so it comes back to its original length. Okay, so that means that it is an elastic deformation. When I remove the stress, it comes back to its original state. So what is happening at the atomic scale? When I apply this force, this elastic deformation occur, in fact, we don't break the bonds. They just we just observe an increase of the distance between the atoms, so an increase of the interatomic distance. And so that means that we will change a little bit this interatomic distance. Okay, so we may increase this interatomic distance. And if we increase this interatomic distance, if we increase it a little bit, okay, to that stage, so in fact, we will increase the energy of the bond will increase. Okay, so depending if I have an energy well that is more deeper or that is more large, that means that the variation of this energy will be either higher if I have a deeper potential energy well than if I have a more larger energy well, because the change of this energy will be different, okay, will be higher in the first case than in the second case. So if we compare, sorry. Okay, if we compare these two materials, so in that case, we represent the force as a function of the interatomic distance, okay, of these two materials, A and B. In order to compare the elastic, what is happening when we stretch the material, we can use what we will describe as the elastic modulus. So it is a properties of material that is associated to the elastic deformation. So the higher elastic modulus and the more rigid is the material. And the elastic modulus is determined by the derivative of the force of this curve, right? At the point where R, the interatomic distance, is equal to the distance of equilibrium, okay? So basically, we should have a look to the derivative of the curve of the material A and the derivative of the curve of the material B when these curves cross the axis X. Okay, and so in this case, we saw that the slip of this derivative is higher in the case of material A than in the case of material B. So that means that material A is more rigid than the material B. Okay, so we have a direct relationship between the energy well and the rigidity of the material or the elastic modulus. Okay, and now I will remove it. And now let's have a look to some thermal properties and the relationship between the bonding energy and first the expansion coefficient. So here also we have two examples of energy curve as a function of the interatomic distance. And so we are going to examine which of them have a higher thermal expansion coefficient. So in fact, this thermal expansion coefficient is related to the fact that when I heat my material, so I will observe macroscopically an increase of its dimension in one specific direction. Okay, so in that case, it is related to the capacity of the interatomic bond to increase. Okay, so to increase the distance separation between the two atoms when I give energy in the form of heat to my material. So when I give heat to my material, I give energy. So the energy is increasing. So what I am going to see is the following. I should consider for each of this material, I should consider the bonding energy, okay? And so I will have a look to the increase of energy that will be given to this material. And so I will have a look to how the interatomic distance evolve with this new energy. So I add the given energy to the energy bonding, and I see what is now, okay, the interatomic distance between this atom. So in the case of this material, it is represented in gray. So when I give this energy to the material, so it results in an increase of interatomic distance corresponding to this distance, okay? Now, if I do the same for the material that is represented in blue, so I give the same amount of energy to them, and I will observe only an increase of interatomic distance corresponding to this distance, okay? So the spacing after heating for this material, the blue one will be lower than for the material represented in gray, okay? So now let's see another relationship between the bonding energy and another thermal property, which is melting temperature. So the materials that have a high bonding energy will exhibit a high melting temperature. So if we have a look either to this table that we already saw briefly, or this graphic that is even more clear, when the bond energy increases, So the melting temperature of the material increase. And so the melting temperature of a material will depend extremely of this bond energy. So let's see. The material that have van der Waals, so it is secondary bond, will melt as low temperature. Then we will have the metallic bonds, and covalent and ionic bonds will result in a material that will have a very high melting temperature. So if you have a look to this table, you will see that regarding the covalent bond, for example, a diamond is composed only of carbon. And so in this material, the carbon are linked together by covalent bond, and you can see the very high melting temperature of this material. Ionic material, so it's depend on the composition and the energy of the chemical bond between the two atoms, but the melting temperature used to be quite high. So you have two examples right here. The metallic material, so metals that are composed of a metallic bond, depending on the metal, we have quite a high range of bonding energy. So mercury, for example, have a melting temperature lower to 0 degrees C, whereas tungsten has a melting temperature above 300 degrees C. And so this is quite coherent with the fact that it is quite coherent with the fact that ceramics and metals will melt at a very high temperature. Whereas in the case of polymers, according to what we observe in this table, it is quite difficult to understand why some polymers can melt at 60 degrees C, or can melt even at 200 degrees C, but at this, so at much lower much lower temperature compared to metals and ceramics, because polymers, the polymers are made of chains, okay, and along the chains, the atoms are linked by covalent bonds. So looking to this example in this table, we should expect to have a higher melting temperature for these materials. But in fact, what is important in polymers is to consider the interatomic, the intermolecular interaction, which means interaction between the atoms of one chain and of another chain. And so what kind of interaction do we find? So it corresponds to secondary bonds, so for example, to van der Waals or hydrogen bonds, depending on the atoms found on these molecular chains. And in order to melt this temperature, in order to melt this material, so the energy should be able to overcome the energy of the secondary bond. And we saw that the energy of secondary bond are much lower than the energy of primary bond. So that's why polymers have lower melting temperature compared to metals and ceramics. So we will see it more deeply in this course. Okay, and if we focus on, if we give some energy to this material that is able to break this bond, okay, this covalent bond, so we will not melt the material, but we will degrade the material, and eventually it will occur the vaporization of this material. So finally, to summarize what we saw in this class, so the materials have a different kind of bonds. So in the case of the polymer, we just talked about it, we will find covalent bonds along the chains and secondary bond between two chains, okay? In the case of ceramics and glass, In this class of material, we will find ionic and covalent bonds and a mix of these characteristics. So covalent bonds with a ionic character. And in the case of metals, we will find metallic bonds. And so to remember, here you have a range of strengths of such bonds. So you can have here an idea of in kilojoule per mole of the strengths of these different kind of bonds. And so I hope that you have understood the different aspects that are very important to understand the atomic structure, but also the interatomic bonds and the relationship between the bonding energy and some of the properties observed in these materials. So if you have any question, you can write me on this email, and up to see you soon. Ciao.